Hello all, I hope all are safe and good. In this video, we are gonna look about the short channel effects on MOSFETs. So let's get into the video. First of all, what is short channel MOSFET? A MOSFET is considered to be short when the channel length is the same order of magnitude as the depletion layer width of the source as well as the drain junction. So the potential distribution in the channel now depends upon both the transverse field due to the gate bias and also on the longitudinal field due to the drain bias. So when the gate channel length is very less than 1 micrometer, the short channel effects comes into play. And in MOSFETs, the channel length must be greater than the sum of the drain as well as the source depletion width to avoid the edge effects. But if this condition is not satisfied, a number of effects may appear like off-state leakage current, impact ionization, velocity saturation, mobility degradation, drain-induced barrier lowering, drain punch-through, surface scattering, and etc. And there are also some of the benefits from this short channel MOSFETs, that is, reducing the dimensions, increase the number of devices and circuits that can be processed at one time on a given wafer. And the frequency capability of active devices continues to increase as the intrinsic frequency values increases with smaller dimensions, while the parasitic capacitance also decreases. So in this video, we are gonna look about a specific short channel effect in detail, namely velocity saturation. So we all know about the digital ICs, where we typically use the transistors with the shortest possible gate length for high speed operations. As the channel length is reduced, the electric field increases if the voltage is constant. And the carrier velocity is also related to the electric field through mobility, and that is given by this equation V is equal to nu E. Nu is nothing but mobility and E is electric field. But at high electric fields, the average velocity of a carrier is not proportional to the field and it does not increase with the electric field. Rather, when a strong enough electric field is applied, the carrier velocity in semiconductor reaches a maximum value, that is saturation condition. So this leads to the earlier saturation of the current, that is before the drain voltage reaches the VGS minus VTH, the current reaches the saturation state. And when this happens, the semiconductor is said to be in the state of velocity saturation. So the velocity in that saturation region is given by this equation Vd is equal to mu E divided by 1 plus E by EC. And we have a degradation of mobility here because of the scattering by vertical field, and that is also called as mobility degradation. And the carrier loses the energy by emitting photons as soon as the carrier energy is large enough. So in this graph, we can see comparisons between the long channel device and short channel device. The short channel device, where the velocity is not proportional to the electric field due to this velocity saturation. So as soon as the VDS reaches the VD sat, it reaches the condition of saturation. The drain current gets saturated. But in long channel devices, only at VDS equal to VGS minus VT, the ID current gets saturated. And the electron drift velocity is proportional to electric field only for the values of electric field less than 1.5 volt per micrometer. And the ID sat is nothing but the saturation drain current is proportional to VGS minus VTH rather than VGS minus VTH the whole square. And the drain saturation voltage is also lower than for long channel MOSFET, and VDS sat is less than VGS minus VTH. So the device enters the saturation before the VDS reaches the VGS minus VTH, and it operates more in saturation region. So due to this velocity saturation, there are some consequences that are arising, mainly in the saturation drain current. So the ID current is lower than the predicted by mobility model, and ID increases linearly with VGS minus VT rather than quadratically in the saturation region. So this equation is given for saturation drain current, where VD sat is nothing but L by mu n into V sat. So that's all about velocity saturation, and I believe that this content would have been more informative and useful to you. Thank you for watching this video.